Diğer Kemal'ın böyle bir suçlu olması lazım.
Okay, so we started looking at some of the implementation and design issues with the paging, paging placement algorithms. One of the issues with the paging was how do we decide on the page size? I mean, should the page size be like 1 kilobytes or 2 kilobytes, 4 kilobytes? I mean, as long as it is to the power of something, to the power of n, it is okay with us. But how do I decide on this n? If we choose the page size large, with larger page sizes, we waste memory. Why? Because let's say I need to allocate a memory of, of 15 kilobytes, and my page size is 4K, okay? If I need a memory of 16 kilobytes and my page size is 4K, then I need to allocate 4 pages. 4 pages makes like 16 kilobytes, right? 16 kilobytes. So 1 kilobyte of memory of the last page is wasted. That's not a good thing. And on the average, the half of the last page will be wasted. Okay, half of the last page will be wasted. Whatever you do, on the average, I cannot do this. Okay, half of the last page will not be used, so it will be wasted. That's the problem with the large page size. If your page size is like 16 kilobytes, then on the average 8 kilobytes of the last page will be wasted. With small pages, you need lots of memory space for the page tables, because you will have many entries. So you need to come up with something in between. It should not be very small, it should not be very large. So there is a formula that we discussed last time we started discussing it. Let's say we have the average process size is S. I mean, maybe my process size is maybe like 1 megabyte. 1 megabyte is 2 to the power 2 to the power, what is 1 megabyte? No, 10 is 1 kilobyte. 2 to the power 20. 10 is kilobyte, okay? 20 is megabyte, 30 is gigabyte, 40 is terabyte, and petabyte. Okay? So I have a 1 megabyte of process size, and the page size P, I don't know, maybe we are going to decide on the page size P. I don't know, it's 1 kilobyte or 2 kilobyte, or I don't know what it is. And assume that each page table entry takes E bytes. So this is a very small number, 2 bytes, maybe 4 bytes, 8 bytes, maybe 16 bytes. Let's say our E is 8 bytes. It is 2 to the power 3. Okay. So we write this formula. This formula says that if you have a process size of S and your page size is P, and each page takes E number of bytes in the page table, and this would be the formula for the overhead. Okay, and this part is for the page table overhead. This is the number of pages in a process, right? We talked about it last time. This is the number of pages in a process, And if I multiply the number of pages number of pages in a process with the number E, which is the number of bytes in the page table entry, so this number becomes the overhead due to the page table, and this number is due to the wasted space of the last page of the process. Okay, last page of the process. Now that I don't multiply this number with all the pages in the process, only the last one, just one with one of them. Okay. So this is the formula for the overhead using pages. Wasted memory in the last page and wasted memory in the page table. And this is my overhead. If I want to minimize this overhead, take the derivative with respect to p and equate it to 0. So if I take the derivative with respect to p, since p is under the division sign here, so this is what I get: SE times p over p squared plus 1 over 2, because p is simply goes away. That would be the formula. And if I say this is equals to 0, then if I derive p from here, isolate p, that would be my formula for the page size. Okay, formula for the page size. Remember we said that take the square root of 2 times, what is the s? S is 2 to the 20 and e is 2 to the 3. So this total makes, if I calculate this one, what do I get? It is 2 to the power 24. So what would you get if you take the square root of it? It is 2 to the power, you take the half of it, 12, right? So 2 to the power 12 is, how much is that? Okay.
4 kilobytes.
So it is 4 kilobytes. Say that this formula says that my page size should be 4 kilobytes with these kind of numbers, and these are typical numbers. If you have larger processes like 8 megabytes or sometimes 120 megabytes, then maybe your page size should be larger. But this is, I mean, it has the assumptions. These are the wasted spaces. There might be other issues too. Maybe, I mean, you might consider, this is only considering the overhead of using the pages, but overhead of using pages might cost you some CPU time too. This does not consider any CPU time. That's the problem with this one. So, I mean, this is not the ultimate formula for deciding on the page size. This just considers only the memory usage, wasted memory usage. Okay, so page size is a common problem, but 4 kilobytes of page size is a very common page size. Sometimes 8 kilobytes is used, sometimes 2 kilobytes is used, but 4 kilobytes is very popular. Okay, another design issue, separate instruction and data spaces. I have my address space for my process. Okay, if I have a single address space, and if my address space is not that large, that may not be sufficient for me. So I might be out of addressable space if my process is very large. For that case, sometimes some operating systems separate the instruction space and the data space, something like that. Okay, this is usually what I have. Okay, let's say I can address this much of memory. Okay, 2 to the power 32. 2 to the power 32. How many megabytes is this? 4 megabytes? Like no, this is 4 gigabytes, right? 4 gigabytes, because 2 to the power 30 is a gigabyte and 2 times 4. This is 4 gigabytes, right? 4 gigabytes of memory. And at the lower end of the memory, my address space, I keep my program. These are my instructions. Okay, these are my instructions and these are my data. Okay, so if 4 gigabytes is not enough for me to keep all the instructions and the data, then I could do this. There should be an instruction space, okay, and there would be a data space. And since now I have all the space for me for the instructions and for the data, there should be enough space for both of them, and I should be fine. If the original space is not large enough, then I could use such a solution. But it looks like I am wasting lots of space. That's the disadvantage, right? Is that correct? I am wasting lots of space in the I space here. Is that correct? Lots of wasted space. Is that correct? I am wasting lots of space. Say yes or no.
No.
Doğru. Muhtemelen. Muhtemelen öyle bir durum var.
So the answer is no. Okay, continue from there. Answer is no. You are not wasting any memory space because we are using paging. These unused spaces does not have to be on the memory, right? Paging only keeps the part of the memory that we are using, okay? So you are not using this part of the, if you are not using this part of the memory, it will not be loaded to the memory at all, so it will not keep any space. That's the advantage of paging, okay? So if you need lots of space, it can provide you lots of space. If you have more than enough, then that paging will be very, very efficient. That's the good part of it. Okay? That's the good part of it. So the answer is no. No space will be wasted. I mean, the wasted space will be only the half of the last. On the average, half of the last page will be wasted because all the others will not be loaded to the memory. Okay, any questions? So separate instruction, okay, and data spaces are good. But nowadays we have more than enough for the address space. We don't use these kind of approaches to get more space for our processes, instruction, and data spaces. But still, for the cache, we might use such an approach because in the cache we don't have enough space, and you might want to use some part of the cache for data and some part of the cache for the instructions, and you might use such an approach for the cache organization. Okay, continue with the implementation and design issues with the paging. Shared pages, okay, shared pages. We never talked about shared pages before, but if two processes have the, if both of them have the same data, they are using exactly the same data, then there is no point in copying the same data to the different part of the memory at all, right? So why don't we share it? So that's what we call sharing pages, shared pages. Okay, pages that are read-only, such as program text instructions, can be shared. I mean, you can have more than one copy of the same process running on the memory. So I don't need to copy the instruction part of the program text part of the process 2 times on the memory. Keep the same instruction part and maybe copy the data, maybe duplicate the data, something like that. Okay? This is my process table. This is my process number 1 and process number 2. These are running the same program. Let's say what kind of program? I am running gedit, and this one is gedit 2. I am running 2 copies of the gedit program. Okay, so the program part is exactly the same, but data part is different. So what do we do? If you have separate instruction and data spaces, then keep the instruction space the same. See, both of them, this one and this one, are using the same instruction space, but their data spaces are different. So it is easy to keep the program text the same. It is to keep the program the text the same when you are sharing the pages. The difficult part is if the data is the same. If I wanted to share the data, that becomes a problem. Okay. So what is the problem? The problem is that if I share the data, if one of them changes the data, the other one will get affected. That might be a problem. Sometimes it's a problem, sometimes not. If you wanted to make some kind of inter-process communication using the shared data, that's okay. But if you want to keep your data to yourself, that becomes a problem. Okay. So using separate instruction and data spaces, if they are supported, then it is relatively straightforward to share the text part of the program. Okay. If you are using shared pages, and the context switch overhead can be reduced by this way, because some part of the address space is the same. Switching between the processes becomes faster because pages are the same, right? Pages are the same. So that's something good. Context switch between shared pages of two processes are good. But sharing data is has some tricks, because you are changing your data. Okay. If you are not modifying your data, both of processes, if they are not modifying the data, then it is okay. You can share the same data pages. If one of them modifies it, as soon as it modifies it, then you make a copy. Okay, you make a different copy. It's called copy on write. Okay, it's called copy on write. Only the data pages that are actually modified need to be copied. Otherwise, they can be shared. If the data is not modified by any of those processes, then it can be kept the same. It can be shared. Okay, so copy on write is a technique where you can share the data segment of your code with other processes as long as nobody modifies the pages. As soon as somebody modifies it, then it makes a copy. It makes a copy and modifies it. Okay. Without any modification, there would be no performance problems. Context switching would be very, very fast. But if you are making modifications, then you need to copy your data. Any questions? Any questions so far? Okay. Let's continue then. Something similar to shared pages, shared libraries. Okay, this is something we keep using all the time. Shared libraries. Okay. Remember, we can in C or C++ applications, when I compile, when I say GCC -o my probe.out, then sometimes I do this. What is -lm? -lm. Link the math library with my code, right? What does this do? This one gets the math functions that I use in my program, and it links it in my program, right? And whenever I call them, it is already in my addressing space. But the thing is that there are many other programs running on the memory using the same library, okay? So the code is the same. Everybody is linking to the same code, and everybody is copying the same code over and over again. So shared library says that if you are sharing some code, okay, some library, then you don't have to statically link those libraries to your code. What do? You keep them the same, and if this process and this process are using this part of the library, they can share this part as the pages. Okay, so there are some pages coming from the shared libraries. Okay, so this program, this process, and this process are sharing the program code, program part. For example, this the function sqrt. Okay, function sqrt is from the math library. It is loaded in the memory. Okay, with its own pages and etc. So my process shares these pages with this process number. This way, I don't have to reload this sqrt function into my process. I don't have to reload sqrt function into my process. That means I am saving lots of memory. I am not loading the same sqrt function many times. I mean, this is a very big problem if you are running on the windowing environment, like with the Windows, because each application has to call some windowing functions. Okay, there are hundreds of them, and each one should not load its own windowing function. Okay, they are calling the same functions using the same by sharing the same pages. Okay, so page sharing is happening again with the shared libraries. Okay, so the shared library shared. This should be shared. Okay, shared libraries are paged. Shared libraries are paged. They have their own pages. but you are sharing those pages between the processes, okay? And shared library routines are located at different memory addresses for each process. For example, these shared pages are here for this process, and they are here for this process. So if my code here says that somewhere jump to address, let's say 30,171, if I say jump to address 30,171, its meaning will be different for this shared pages, and its meaning will be different for this pages, so that's a problem. So for the shared libraries, we cannot use these kind of absolute addresses, okay? We cannot use these kind of absolute addresses. Instead, for the shared libraries, we use position independent code. Position independent code. What do I mean by position independent code? You don't give any absolute addresses, okay? You give addresses like, okay, jump to location like 10 bytes above my location, okay? So you give only relative addresses, not the absolute addresses, but the relative addresses, okay? So you don't say 30,000 something. You say jump to an address like 100 bytes above me or 100 bytes below me. So you give only relative addresses. That makes it possible to use between these two processes. Okay? That's one problem with the shared libraries. You cannot use absolute addresses with those. But I mean, producing shared libraries is the responsibility of the compiler. When you say the compiler, this is a shared library, it produces code that way. It produces the code that way. Okay? So you know how to make the shared libraries, right? With the C++ and C. They taught you in the C classes and C++ classes. They teach you how to, right? How to make dynamic libraries and the static libraries. Say yes. I know they did. I asked TAs at least 1,000 times, and you know. Yaptınız değil mi? Biliyorsunuz değil mi? Yaptınız ama ne? Yaptık.